So there is a challenge that most engineers face while releasing their models in the production environment. This is not regarding the model itself, but how they serve it. In a production environment, usually you don't serve one person using one device, using one model, but you serve thousands of users with multiple models built in different frameworks in a server. So this is where the lag comes in, the network goes off. So that's where the NVIDIA Triton comes into the picture. So today in this video, we are going to discuss about NVIDIA's Triton architecture and discuss how they actually try to solve this problem and how they design and plan this architecture to precisely solve this problem to face multiple users using these multiple models built on multiple frameworks. And we will be referring to the official documents of NVIDIA Triton, so we won't be missing much of the factual information available on the internet. Let's start with this diagram. It's the cleanest way to understand what Triton actually is. On the top, you have the clients. These are your applications, your web services, your mobile backends, data pipeline, whatever is making the inference request. They send us those requests over one of the three interfaces, HTTP, REST, gRPC or CAPI. This request comes into the Triton server and immediately hit a per model scheduler. This is the critical design point. There isn't a global queue. Each model has its own dedicated scheduler, which makes the system horizontally composable. You can tune each model's processing behavior independently. The scheduler then optionally batches those requests together and passes them to the backend. The backend is framework specific execution layer. It's what actually runs the model. TensorFlow, PyTorch, TensorRT, or Nets each have its own backend. The backend takes the batched inputs, runs inference, and returns the outputs. Those outputs go back through the scheduler and out of to the client. That's the basic loop, but now let's look at the component in depth. This diagram illustrates one of Triton's most important architectural properties. Multiple models or multiple instances of same model can execute in the parallel on the same system as at the same time. Look at this figure. Two models, model 0 and model 1. Two requests arise simultaneously. Triton schedules both onto the GPU simultaneously. The GPU's hardware scheduler runs both computations in parallel. That's the default behavior across different models. But what about multiple requests for the same model? By default, if multiple requests arrive at the same time for the same model, Triton serializes them. It runs one, then the next. That's because each GPU has fixed amount of resources and native serialization is the safe default. But you can override this. The Triton has a configuration option called instance group. It lets you define exactly how many parallel execution instances each model is allowed to use. The block here shows the model 1 configured with 3 instances. Look at what happens. First 3 requests of the model run simultaneously. The fourth one has to wait, but only until the one on the first 3 ends. This is how you take the GPU that's sitting in 50% utilization under naive serving setup and push it toward its actual capacity without changing your actual model. And it works equally for CPU inference. The same design applies with system-wide scheduler handling the thread execution. Triton supports multiple scheduling algorithms, and which one applies to a given model depends on the nature of that model. NVIDIA's architecture gate breaks this into 3 categories: stateless models, stateful model, and ensemble models. Let's take each one. The stateless model is one where each request is completely independent. There is no memory carried from the inference to the next. Classical examples are convolutional neural network, image classifiers, object detectors. You send in an image, you get the prediction. Nothing is remembered about that request once it is done. For a stateless model, Triton uses either the default scheduler, which processes the request individually, or dynamic batcher, which groups requests from multiple clients onto a single batch before sending it to the backend. Dynamic batcher is particularly valuable here because stateless models are the exact type where batching pays off most. The GPU processes a batch of images in roughly the same time as it processes one. So batching directly multiplies your effective throughput. Stateful models are a different story. These models maintain in their internal state between the inference request. Each request in a sequence build on the previous one. The classical example is recurrent neural network handling a time series or a conversational AI that remembers that you said 2 turns ago. The challenge this creates architecturally is this. If requests for the same sequence land on different model instances, the internal state is lost. The model has no memory of the previous request. Now Triton solve this with the sequence batcher. The sequence batchers ensures all requests in the sequence are routed to the same model instance. It uses something called correlation ID, a unique identifier that the client includes with every request in the sequence to track which requests belong to the together. On top of that, the sequence batcher communicates control signals to be the model itself. It tells the model when a sequence is starting, when it's ending, and when a request within that sequence is queued and ready to execute. This lets the model properly initialize its state at the start of the sequence and clean up at the end. These control signals start, end, ready, and core ID are passed as input tensors to the model. The scheduler sets them automatically. The model reads them to manage its lifecycle correctly. So most real-world AI workloads aren't a single model. They are a pipeline, pre-processing, then inference, then post-processing, or sometimes multiple models running in parallel and merging their outputs. Triton's Ensemble models feature was designed specifically to handle this pattern inside the server without requiring the client to orchestrate the steps. An ensemble model is defined as a pipeline of models and the data flow between them. It is not a model itself, it's a scheduler that describes how data flows between the underlying models. And here is how ensemble schedulers work step by step and as described in NVIDIA's architectural docs. First, the client sends a single inference request to the ensemble. The ensemble schedulers receive the input tensor and recognize it as starting point of the pipeline. It checks the internal model it's supposed to receive that tensor. It sends an internal request to that model and pre-process the pre-processing model. When that model finishes and returns its output, the ensemble scheduler collects the result and maps it to the next model's input tensor. It sends another internal request, this time to the classification or segmentation model. This continues until all steps are completed. From the client's perspective, they send one request and got one response. The entire multi-model pipeline can run inside the Triton. The data never left the server between the steps. Intermediate tensors are kept in the shared server memory. There is no serialization overhead, no network round trip between the models. And each composing model inside the ensemble can still be individually scaled with its own instance group settings. The ensemble scheduler itself is event driven and extremely lightweight, so it's almost never a bottleneck. You scale the individual models, not the ensemble. So Triton's architecture is built around a few keys like inference requests sent over HTTP, gRPC or C API and are routed to per schedulers, no single global queue. It has concurrent model execution, allows multiple models and multiple instances of the same model to run in parallel and dramatically raising the GPU utilization. Schedulers handle stateless model, stateful model, dynamic matching, and with sequence batching with correlation IDs to preserve the model state across a series of requests. Ensemble model lets you define multiple entire multi-model pipelines inside the Triton with data moving between the models in shared memory, not over the network. So if you want to dig deeper, you can check out the official link of NVIDIA Triton. The architecture guide is in the description. It's worth reading end to end. It's actually, if you are you can actually evaluate the Triton for real deployment. In next video, I'm going to tinker with new steps and dive deeper into the NVIDIA CLI or DLI deep learning inferences part or NVIDIA GPU functionalities and all. So if you like how I tinker with stuff, how I present to you, I will actually request you to like this video and subscribe to my channel. and stay tuned.